Log on, tune in, find out. Another good idea from Cambridge.
Yes. Okay, makes no difference anyway. So if I quote Tony, say that if you're in a place where you know half of the people, it's a good sign. I think I know 5% of the people in this room, so I'm not so sure if it's a good or a bad sign. We'll figure out later. So I'm affiliated with École Centrale de Paris and École de Pont, joint appointment, and I'm also scientific leader of an area group at Paris. This is joint work with Nikos Paragios, who did most of the optimization part, which I will present. And the applications are work of Xianbo and Xiaohui Wang on the segmentation of the vertical, and Ben Glocker and Aristoteles on the registration. And hopefully I will be able to run a live demo on the laptop. So usually what we do in medical imaging is a fairly standard paradigm, which is the case also in computer vision. We try to extract image-based biomarkers, and the idea is somehow to answer a clinical problem. So, the image is very dark. Yeah, I think it's the connection. I mean, I have changed my resolution. Okay, that's my resolution. So if I can get my screen back. Okay, I'll duplicate. Go ahead. It's in French, right?
Yeah, that's fine.
I think it's in English, the menu. Okay, now it's much better. Fantastic. Thank you so much. So what I was saying is that what we usually do in medical imaging is we try to answer a clinical problem. And this process involves three components. The first is going to try to parameterize our problem with some mathematical model. The idea is that we're going to define some parameters which we'll try to estimate, and eventually, if we can estimate them properly, we should be able to give answer to the clinical problem. So this is what we call the model. Then, once you have these parameters, the task that you will do afterwards is to somehow relate the parameters that you're trying to estimate with what you observe, and these are your images. This is happening with what we call the model-to-data association, and eventually, once you are done with that, then you have to optimize your model and be able to get the best set of parameters which express or explain in an optimal way what you're observing. So if I take a concrete example, this is the segmentation of the left ventricle on CT images. A very naive approach that I used to consider 15 years back is to parameterize your surface as a collection of points. Then once you have this collection of points, what you're going to do is going to define a data term, which eventually you're going to look for edges. It's going to try to move the surface in edge points. And once you have this energy function, what you can do is you can minimize it by taking the gradient with respect to the position of the points, and then you are done. So what is the problem with these methods, and why medical imaging is keep failing despite so many money invested from NIH and European agencies? There are 4 reasons. The first one is what we call Kirchhoff dimensionality. And the idea is that if you want to be able to have powerful models, you have to put it in a lot of parameters. By increasing the number of parameters, you are increasing the complexity of your problem, and therefore the inference becomes almost infeasible. Anyway, let's assume that we solve that. We have to worry about the curse of non-convexity. Our cost functions, our objective functions, are ill-posed in the sense that we have more parameters to estimate than the constraints. And if you don't start from the solution, which is very close to the optimal, you're going to end up with suboptimal solution. Assuming that we solve that, then we have to worry about nonlinearity in the sense that the parameters we try to estimate and the data are related in a nonlinear, highly nonlinear fashion. So exact inference is not feasible. And the reason why also we didn't make it to clinical practice is what we call modularity. That means we spend a lot of time on investing solutions, on figuring out solutions for very specific problems, which unfortunately cannot be ported to other clinical problems. And therefore, every time we have to reinvent the wheel. That is the idea. So this is the reason why, despite millions of papers in medical imaging, very few methods made it to clinical practice. People do use them from clinical research, but very, very few of them, they just, you have a radiologist looking on the indices that he got from the computer and making a diagnostic call. So this here is what I'm going to present. Eventually, if you have in mind, 5 years back, I will have talked about conformal geometry, but now I'm going to talk about something different. So I'm going to talk about graphical models. What is the idea of a graphical model? It's a graph structure where you have a set of nodes, a set of connections, and a cost function. Nodes correspond to the parameters we try to estimate. That's the idea. Connections correspond to dependencies between these parameters, and they model how these parameters should interact. The task of a graphical model consists of optimizing a function, which usually involves 3 terms. There is a term, that means we try to associate to every node a label which corresponds to the optimal solution for our problem. There's going to be a cost which is going to tell us how good is the label with respect to our data. And this usually comes from your observations. Once I have defined this label, I'm going to have a second label, a second term, which is going to measure how well 2 variables agree on the behavior of the model that I'm trying to model. I'm going to try to model dependencies such that I'm getting consistency between the solutions of different nodes which are supposed to interact. And I can go even further and introduce the notion of higher order potentials, where I'm going to have multiple nodes of interacting towards it producing very, very complex behavior. So this is a very common formulation that is not only used in medical imaging, it's used in computer vision, computer networks, and many other files. Of course, this is not new. I mean, people talked about graphical models in macro-quantum fields at the beginning of 80s when I was at the elementary school, and there are some methods that at that time used to optimize cost functions. The first were deterministic algorithms, which were suboptimal methods, very local, and cannot stand to the case of medical where we need very precise solutions. There were non-deterministic methods like annealing and Milford and simulating annealing, which in theory they do guarantee optimality, but in practice it's almost impossible to reach this optimality because of the fact that you have to use the temperature properly. The reason why these methods became very popular at the beginning of 2000 was mostly thanks to the development of graph-based methods and belief propagation. And these methods, under certain conditions, they provide guarantees on the optimality property. Let's now look on the complexity of the problem. So what makes the complexity of a graphical model is the way that terms interact. So if we have, just going to show everything here, if we have a model where the interactions between pairs of variables are linear, then we can guarantee that we can get the optimal solution in a reasonable combinational time. When we move to pairwise interactions which are metric, I can guarantee that I'm going to get a reasonably good approximation of the global optimum. Of course, what is happening in real cases is you are going to have arbitrary interactions, which is going to make the problem to converge to local optimum, and eventually it's going to make really hard the problem, the solution of the problem. So what we would like to do is the following, is we like to move as possible on the right side of the horizontal axis, and we would like to move down as possible on the vertical axis. That is the idea. But as I mentioned before, these are fairly complex problems. So how we can do them? We're going to use a very principled way and very standard way in mathematics. We're going to use relaxation. And the idea of relaxation is instead of solving a very simple problem, so this is an elementary talk. So I have an unit function. I'm trying to figure out the minimum. If I start from a local minimum and I use gradient-based method, I may end up in a local minimum, which is shown here. So I'm going to forget about this problem, consider a relaxed version of it, and I'm going to discuss how we can get this relaxation. And I'm going to hope that the solution of the relaxed version will going to be close to the solution of the original problem. And once I have that, I'm going to have a reasonably good approximation of my optimal. That is the idea of relaxation. So now I'm going to talk about my own contributions. So we did look on linear programming, which is something fairly standard and well known. So what you have in practice is a minimization problem over a discrete set of variables subject to some constraints. And x are our variables that we have to estimate, and a times x equal with b are the constraints. This is a very common relaxation because there are very efficient optimization algorithms to be used. And also we can use other combinatorial algorithms. So the question is how we convert a graphical model to an LP. I'm not going to explain to this formula, but there's a very simple standard way of converting any macro-quantum field, any graphical model to a linear programming problem. What you have to do is to introduce artificial variables, which is going to be the variables corresponding to the LP problem, and introduce constraints, which will impose a constraint that every node will get a single label, and there's going to be consistency between labels which are supposed to be connected. So this is standard. Any MRF can be mapped to an LP problem by using this kind of formula. Now, we have our LP problem. we have to worry about three things. First of all, you have to be computationally efficient. Second, you have to be able to guarantee a very good solution, if possible and optimal. And third, you have to be able to extend it to higher order cases, which is very important. Let's look about computational efficiency. If we consider the original problem, we know it's NP hard. That means that the agreed solutions cannot guarantee the optimality, and at the same time, they require computational time. So what I'm going to do, the first thing is to relax my problem. Instead of solving my original problem, which is fairly hard, and assumes that x is supposed to be an integer value, I'm going to consider the same problem, but I'm going to relax my constraint with respect to x. Okay? And this is going to define my primal LP problem. Once I have my primal LP problem, I know from the linear programming and the duality theorem that I can introduce or I can define an equivalent dual problem. The dual problem is going to be a maximization problem. It's going to act on a new set of variables y. These two problems will share the same constant coefficients. Okay? And if there is a unique solution with x, there's going to be a unique solution for y, and I know how these two solutions will be related. So this is something fairly standard. So if you can solve your primal, then you are able to solve your dual as well. Okay? And we know that the optimal solution is going to be in between. Remember that this is a minimization problem, this is a maximization problem. That's fairly important. So I'm trying to figure out a way now of solving both problems instead of solving my original problem. So, as I said before, we try to minimize the dual, we try to maximize, we try to minimize the primal, and we try to maximize the dual. And we know that the optimal solution is in between. And we know how this solution is related with respect to an F-star approximation of the integral solution. Since solving either the primal or the dual is fairly difficult, we're going to forget about them. And we're going to introduce a new idea, which consists of defining a problem aiming at minimizing the gap between them. That means if I can generate solutions for x and y, which from one iteration to the next minimize the gap, I know, since I know that the optimal solution is going to be in between the gap, I know that I'm going converging towards the right solution. So I'm going to define a new problem. I'm going to forget completely about my original problem, which was the primal and the dual LP. I'm going to define a new problem which only tries to minimize the gap between my primal and the dual. And what is the advantage of doing that? Is that I'm going to get benefit for the dual from the current solution to the primal, and I'm going to keep iterating. That means every time I improve one of the solutions, it's going to help me to get a better solution to the second problem, and eventually I'm going to get a very good solution by small improvement. And this is the idea here. I start with an initial guess about x and y. I minimize my dual. I use the constraints to minimize my I maximize my dual. I minimize my primal, and I'm keep iterating. So what is going to happen at some point is that I'm not going to be able either to improve the primal or the dual. Okay? And this is going to be the gap, which is going to give us an approximation of the solution. But I know that every iteration is improving my solution. And opposite to the original problem, which was NP hard, minimizing this gap can be done fairly easy. That is the idea. So how this compared with state-of-the-art methods? I mean, alpha expansion is what people have been using. I mean, which is based on max flow principle. So the idea is that you can do something like 10 times faster and as running time, while the iteration, while at the very beginning is fairly expensive, because I get a lot of benefit because of the interactions between the primal and the dual. At some point, the cost of iterations becomes almost zero. And now I'm going to try to run a live demo on a medical imaging problem. Okay. Okay. So this is the problem of the formal image fusion. I have two volumes. What you can see here are the different slices of the volumes. And I'm using what we call checkboard visualization. That means I'm taking a block from the first volume, and I'm displaying a box from the second volume, and I keep iterating. Okay, so what is going to happen is, since the two volumes are not registered, you're not going to see any consistency. And this is how the results look like on the whole volume. So I'm going to run a live registration now on this volume. You're going to see on the fly how the two volumes are deforming such that we get perfect mapping. Okay, so you can see in the process. Then I'm going to show you the results of the whole volume. Okay, we're done. So now I can go here. I can remove that. So these are the results, the same visualization after the registration. That means that I have replaced my target image with a deformed target. This is where we were before. And this is where we are now. And this is the formation field. What?
What's the method you're using?
That I'm going to come to that later. So means let's go back to. I'm just going to show the running times. I'm going to explain the method later. But what is important is to the optimization time. This is the fast primal dual principle. It took less than 0.2 seconds to optimize our model, and we have something like 10,000 variables, and we have plenty of labels which correspond to the deformation. What is the advantage of this kind of methods is that since you don't use any gradient of your energy, you can easily replace your registration criterion with any of the existing known criteria. The optimization will remain the same. The only thing will change is how you construct your graph. Okay, so I can plug in any metric here you like. I can plug any of the known metrics like sum of square differences, corollary ratio, mutual information, or I can derive a new metric. This is not going to change anything at all on the process. That is the idea. Okay. Just going to run once more, and then I will go to the next slide. This is running on my laptop. Okay. We are done. Okay. Now, we have computationally efficient solutions. The question is, can they guarantee optimality? And the answer, unfortunately, is not. Why? Actually, what we're trying to do is we try to minimize the gap between the two energies. We try to minimize the gap between the minimum of the primal and the maximum of the dual. So at some point, since we are doing a relaxation, that means we approximate our original problem with a relaxed version. If the relaxation is not good, even if we get the solution very fast, the gap will remain very important. That means that we're going to have a very bad approximation. That means that we're not going to have an optimal solution. Now, what can we do to improve this, to address this issue and get better optimality guarantees? So I'm going to try to approximate the same problem with tighter relaxations. What is the idea of tighter relaxation? Is that instead of having a fixed relaxation that coming from the LP, I'm going to try to derive dynamic relaxations from on the fly, which at every step is going to try to improve the way that my LP formulation approximates the original problem. And if I can do that, if I can have better and better relaxations, tighter and tighter relaxations, what is going to happen eventually? The gap will decrease, and I'm going to have a guarantee that at the end, I'm going to have the global optimal. That is the idea. How I can get tighter relaxations? Again, I'm going to go back to my original graphical model. I'm going to approximate it with the standard LP. This is the same formula like before. I didn't change anything. Now, I'm going to define a series of dual relaxations. Let's assume that G bar corresponds to my singleton potentials, F bar corresponds to my pairwise potentials. This is what defines the relaxation, the potentials themselves. I'm going to create a block with at every step is going to try to change F bar such that my relaxation gets better. That means that instead of having only as unknowns the labels that I'm trying to estimate, I'm going to also introduce the notion of modifying my pairwise potentials, because the pairwise potentials are the ones which actually define the complexity of the problem. So if I have a better approximation of my pairwise potentials, then I'm going to have a tighter relaxation. That is the idea. So I introduce a new minimization problem, which I call D plus of G bar and F bar, where G remains as it is, because it does not involve the complexity of the problem. And I'm replacing F bar with a new F that I can change. So F is going to be a new variable that I will introduce, and will correspond to how good is my relaxation. The only constraint I will impose for F is that F should satisfy, with respect to some criterion, the original pairwise potentials that I had at the very beginning, which is F bar. Okay, so I'm trying to generate a new approximation of the problem. The way I do that is by modifying my energy, and I'm only imposing global constraints on the way that this modification will happen. So if I can solve this problem, then I can get better lower bounds because of f, which is now a free variable, and therefore I'm going to get a tighter dual relaxation. How I'm going to solve this problem is the following. I'm going to start with an initial guess. Once I have the guess, I'm going to consider a subset of edges. For this subset of edges, I will allow myself to change the potentials such that it satisfies the global constraint. Once I have the new potentials, I'm going to solve the new problem, which is a tighter relaxation, and I'm going to keep iterating. So at every step, what I do, I select a subset of variables. For this subset of variables, I approximate my problem in a better way, and I'm keep iterating. Okay? So if we do that, what we have as guarantee is that the extra set of variables, which we call virtual potentials, will help us to get a tighter relaxation, and also it's going to introduce extra constraints, which will force the solution to be the optimal one. That is the idea. I'm just going to show you the algorithm. So we start with an initial guess where the pairwise potentials is the one we observe. We solve our problem. Once we have solved the problem, we consider a subset of variables in this problem. For this subset of variables, we re-estimate virtual potentials, which produce a tighter relaxation. Once you have these tighter potentials, we initialize our initial problem, and we keep iterating. So at every step, what you are doing is you're considering a subset of your problem. And for this subset, what you do is you improve the way you approximate your original energy with your LP formulation. And since you improve your relaxation, this automatically means that you're going to get a tighter bound, and it means that you're going to get a better solution. That is the idea. And the way you choose the subset of edge can happen arbitrary, or you can use what we call cycling repairing, which I don't have time to explain. So this is what is going to happen. At the very beginning, we are here. We use the original potentials we had from the problem. Once you have new potentials, you're going to get the lower bound. This lower bound will keep improving, and we're going to keep iterating. And you have a guarantee at the end that actually this will converge to the optimal solution. Of course, the way that you're going to change, you're going to consider your subset of edges that you're modifying is going to affect the convergence. So if you don't do it intelligently, you have to maybe iterate forever until you get the optimal solution. But there is a theoretical proof that this framework will converge to the optimal solution. And there is also a proof that this is equivalent with what we'll call the tree-weighted optimization. So this is a better way of getting optimal solution, but it's fairly expensive. So how I can go further and use the same ideas for higher order models. The idea of higher order models is that I don't have only two variables interacting. I have more than two variables that can interact, and this is going to allow me to do more complex behaviors. I'm going to use the same idea, the dual decomposition, again on the LP space, the duality. And the reason why I have to go to high order is because pairwise are fairly simple. There are very efficient methods to optimize them, but they cannot reproduce very complex behaviors. Okay? So higher order can capture multiple interactions, allow for more expressive powers, and can produce much more accurate modeling. So there is a real need of being able to have all variables interacting, and this is usually what happens when you have a continuous formulation. There is almost no work on higher order optimization, and this is mostly due to the fact that these are really hard problems to optimize, and unfortunately the computational complexity goes to infinity, because when you have to combine more than two variables, then the combination of the labels also explodes exponentially with the click size. So what we're going to do is again go back to the duality and try to figure out a way of solving this kind of problems. I'm just going to recall what is a higher order model. A higher order model consists of a graph where nodes have their own potentials, and then I have more than two variables interacting. That's a higher order model. Okay? And this is what we have here. This is a higher order click. And this is the problem, how I approximate this higher order click. Let's keep that. So the dual decomposition is a fairly simple idea, which consists of saying that instead of trying to solve a very complex problem from a single person, which is really hard to solve, I'm going to try to decompose my problem into subproblems. These subproblems will somehow share variables, And then I'm going to ask different persons to solve the individual problems. So I'm going to have a master, which is going to have a global view of the problem. And then I'm going to have, for the individual subproblems, different solvers, which are going to try to produce optimal solutions for these subproblems. Okay? So the problem is that the different slaves share variables. So that means that I'm going to have, for the same variable, different solutions. So the role of the master, the work of the master, will be to coordinate, to do a coordinate descent on the variable space, such that at the end, every individual solves its problem optimally, and the global solution is consistent, in the sense that when I have a shared variable between different slaves, I get the same estimation for this shared variable. That is the idea. So how I'm going to do that? I'm going to have a hypergraph which has the global view, which is here. This is my master. And then I'm going to just decompose the way I want my problems, such that every slave gets a subproblem. And if I take the union of all slaves, I have my original problem. Okay? Many other choices exist as well. So the way I'm going to impose the consistency is the following. At every iteration, slaves solve individually their problems. They send back their solutions to the master. And the master is going to change the energy such that, as a function of time, this energy converts to the same values for variables which are shared between different slaves. So you get a solution, you send it back to the master. Master changes the energy using the dual principle, sends it back to the slaves, and you keep iterating. And then that you're going to have every slave converging to its own solution, and this solution will be consistent across all slaves, and you're going to have a guarantee that this solution is also a good optimum of the global problem. That's the idea. Yes, you are exchanging. Actually, belief propagation, I mean, so we prove that this is a generalization of belief propagation. Okay, so the idea is fairly simple. The master talks to the slave, sends the energy components. The slaves solve the problem. They send back the labels. And then the master, what it does, it takes these labels and it's going to update the potentials using Lagrangian subgradient approach, such that as a function of time, all the potentials converge to the same solution. That's the idea. So it's based on message passing, and this is working fairly well. And we can use any decomposition we like of the original problem with respect to the slaves. So what is the advantage? How are we going to do this decomposition? I mean, the only constraint we have is that if I take the union of all slaves, I should be able to produce my original problem. But if we use difficult slaves, that means that every slave is solving a really difficult problem. That means that I'm going to have a tighter lower bound for this slave, and the sum of all lower bounds is going to be the lower bound of my whole energy. So you have the interest of decomposing your problem into subproblems where each subproblem is very difficult to solve, because this is going to guarantee that you have a better lower bound for the individual slave, and eventually this is going to also guarantee that you want to have a tight dual Dirac section for the whole problem, because you're always working on the primal dual space. That is the idea. So a very simple and generic way of optimizing higher order MRFs. We can consider that every higher order clique is a slave, or is a slave, and then every higher order slave is solving its problem, sends it back to the master. The master updates the potentials using the subgradient approach and send it back. And you can use any minimizer you would like for the individual subproblems. Means you just have to send me back the solutions. It can be a continuous, it can be a discrete. The only thing that the master needs is to get back the solutions. Then he's going to re-update his potentials and send them back. So it's a fairly flexible framework, because the coordination between the different slaves is done from the master. So you get the coordination for free. The only thing you have to do is just to define individual slaves which are able to solve very tight problems. Now I'm going to go to applications. I have 15 minutes. So the first is image segmentation, which is fairly simple to what was presented before. A standard formulation for image segmentation is to look on the maximum posterior probability. That means that you are looking for a map omega, and then you have observation, which is the image. This is a typical example of the left ventricle. And what you can do is you can decompose your map as a product, or you can approximate it, of the conditional density of your image given your segmentation times the prior you have on the segmentation. So there's going to be a shape term, which is a prior. Then you're going to have the image likelihood, which looks on your expected characteristics of the different parts of the image. Now you have that, and this is something that Tony has worked a lot and his colleagues. So the way that you define the data term is by looking on two measures. The first one is a data likelihood. So you like eventually that all the pixels that are attributed to a class have strong likelihood with respect to this class. So you integrate along all the different classes with respect to the expected likelihood, and you take the minus log of that. That's usually what we call the regional term. And then you have a second term, which is a boundary term, which simply states that on the where you position your surface, your separation surface, you should have strong gradient. And you can measure the gradient by looking either on standard conventional ways, looking on the image itself, or looking on probabilistic weights for the gradient. But this is a fairly simple way of expressing all existing boundary and image terms. You have an integral of the region, and then you have an integral on the surface, which you look for boundaries. Now I have that, so I can express my energy as a sum. Again, this is just an example of the left ventricle. There's going to be a term corresponding to what we call the blood pool here. There's going to be a second term which corresponds to the myocardium, which is the area between the blood pool and the heart. And there's going to be a last likelihood for the background. Okay, so if I divide by the background likelihood, then I can get rid of the other terms. Now, how I'm going to introduce the prior? I mean, there are plenty of methods. Since we're looking on a graph-based formulations, we like to have priors that can be learned from very small number of examples. So I'm going to look on distances between points. So the idea is that if I measure the distance between 2 points, just Euclidean distance, okay, then this distance normally should be preserved, subject to scale. Okay, that means that if you somehow if you look on all hearts, or if you take a huge data set of hearts and you normalize them to the same scale, normally the distance of 2 corresponding points should remain the same, approximately. So what we're going to do is introduce probabilities that will measure the relative distance on the Euclidean space between any 2 points of our model. We're going to have a point-based representation, and this point-based representation is just going to look on how this distance evolves in a huge data set. And this is going to be what we learn. And if we want to introduce scale invariance, we can divide this distance with a set of all distances. So you take every 2 points of your model, you connect them with a link, and this is my pairwise term. And the way that you expect the way that you define the cost on this link is by looking on the deviation of the corresponding distance with respect to what you have learned from your training set. Okay? So you can decompose your prior as a product of pairwise terms, which will take every 2 points, and it's going to use this set of points to measure how consistent is your solution with respect to what you have in your training set. And this is the user defined, so you can have, at the very beginning, you just define an arbitrary set of control points. This is your model. Our model is a point-based representation. So you segment it with the level sets, and then you just uniform apply points. You can have any number of points. The idea is that you just look on relative distances between 2 points. Sure. Now, my graph is going to be every node will correspond to the position of a point that I have used to represent my solution. My pairwise terms, they're going to correspond to the boundary term and the regional term, and the connections will correspond to how well I preserve my prior. That is the idea. The only problem is that since I have a regional integral, it's really hard to express this regional integral when I use points. So I'm going to use the divergence theorem, and I'm just going to convert my regional integral to a product on the surface. And then I can have also the regional term on the pairwise potentials. So this is just the divergence theorem, the Green's theorem. So if you do that, you can put that on your graph-based model. We have used tag imaging because it's more challenging than conventional images because you have some texture. We used 60 images cross leave-out validation. That means that we learn using 51 and then you test on the 60th, and you keep iterating to do that 60 times. We have a 0 point that it takes something like 0.8 seconds per image, and we compared with the most well-known competing methods, which is actually the one is active shapes, and the other one is something what we developed is based on graphs. So this is what we call the dice coefficient. That means that what is the overlap between the actual solution and the obtained solution, and the size of the box corresponds to the variance. Okay, so means we're doing fairly well. Now I'm just going to use a second example, which is the demo that I just showed you, is the idea of registration. So in registration, we try to figure out a way of mapping one image to another, and of course you have to do it efficiently. You have to take into account dimensionality. You have to be able to use different matching criteria, because depending on what kind of images you have, you're going to have to adjust your matching criteria, and you have to be able to adjust different transformation models. So we combine this idea of iconic and geometric registration on a graph-based framework. I don't have time to review that, but I'm just going to give you the idea. So the idea is that you use a point-based representation, and this is going to be the geometric component. Then you're going to try to figure out for every point what is the best point in the second image, and this is just shape matching, by using simple geometric constraints like distance preservation, and that's shown here. So you try to figure out what is the mapping which actually will produce same distances between the two shapes. Once you have done that, then you're going to do exactly the same thing with the image term. That means that you're going to try to figure out a way of imposing the constraint that every point is moving in the second image such that the overlap between the default image and the target is optimized, and you're going to put that all on your MRF. Okay, it's going to be a pairwise MRF, and this is the demo that I showed you earlier. So these are examples. We're going to use any deformation model. We're going to use any metric, because the optimization does not depend on the metric, and you can use any number of control points. The only thing we have to worry is how we're going to impose consistency between the solution we're getting from the iconic term and the solution we're getting from the shape matching. So we're going to couple these graphs with a layer, which is just going to measure the deviation between the deformation produced from the shape matching and the deformation produced from the iconic registration. I'm just going to show you results. So this is done, and I'm going to run again a demo on brain data if you want. Okay. So this is a data set where you have a ground truth. What you are seeing on the left side is the distance for the landmarks. That means that this is the actual distance on millimeters. If we just do iconic, that means if we just look on the data term, and this is standard deviation. This is if we combine landmarks with image terms, and this is also the case if we increase the number of landmarks. So you can see that there is a significant improvement on millimeters by combining these points, by combining shape matching with registration on a unified formulation, which can produce the optimal solution. Just going to conclude. So I'm convinced that graph-based methods is the answer to medical perception for the following reasons. First of all, we can do fairly well in order to reduce to address the problem of chaos of dimensionality by decomposing very complex models to sub-problems by using higher order cliques. That means that you don't have to solve a very complex problem. You can have a very complex formulation which we're able to decompose into sub-problems, and this is can be solved. We can deal with the nonlinearity fairly well because of the fact that means the energy function that we're optimizing and the optimizer does not depend on the data itself. That means I can plug in any data I would like. It's not going to change my optimization process. It's just going to change the way that the graph is constructed. We can do very well on the curse of non-convexity, either because we can guarantee tighter relaxations, or because we know in advance that usually discrete methods are doing much better than continuous one under the same initial conditions. And of course, we can do very well on the monomodularity, because as I showed you earlier, you can plug in any metric. So if you move from one application to another, you just have to adjust your data term. And this is fairly easy. What we're not doing well. Okay. I I think that the future is going to be higher order models, almost convinced. I think also the future is going to be message passing, like belief propagation. And this is going to run on parallel architectures, like graphic cards. It means now with a graphics card, you can get something like 10 times the power you can get from a conventional CPU if you have a reasonably well parallelized algorithm. And I think also the future is going to be graphical models that we learn. That means now we just focus on inference, but we have a number of parameters that's part of the problem. So the future will consist of learning these parameters as well, not only optimizing an energy that we define, but using a huge training set to learn the actual set of parameters that correspond to the optimal solution. What is the problem with medical imaging? First of all, since there are not people doing medical imaging here at Core, I can say that we lack from theoretical contributions. That means that what is important is not how you solve your problem, but what is the clinical problem you are solving. If you have the best threshold method that is solving a very interesting clinical problem, then it's highly likely that the paper will get accepted. So we're lacking for theoretical contributions. We are focusing more on the problem itself and the validation than the way the method we use. But at the same time, I think we're suffering on proposing methods that can be used in a real setting. It means that if you go to a physician and said, I have a perfect solution, but requires 1 day to segment the ventricle, he will tell you, thank you, but I can do it in 15 minutes myself. And even if we ask for 1 day, it's highly likely that we're not going to get a good solution. So the physician anyway has to end it. And the most important limitation is that this transfer between clinical research and clinical practice is missing. It means there is a huge gap. We publish a lot of papers, but very few of these ideas and very few of these methods, they make it to hospitals. Thank you for your attention.
I have a question about the images of left ventricle that is. So your assumption is that the distance is not changed, or?
Yes.
I'm confused because heart is an organ which always moves.
That means if the organ is moving?
The heart is always pumping, right? So
Yes, the heart is pumping. But usually what we do is, for this example, we are looking at systole and diastole, because that's what really physicians care. And even if the heart is pumping, if you normalize these distances with respect to the global volume of the ventricle, there's not much of difference. So it's still kind of preserved. It's not perfectly preserved, but it's not far from being preserved.
You're not using gated images?
You're
not using, how they call that, gated images?
No, we're not using gated images. Actually, what I didn't present is now we moved from that, and now we're using a third order click. That means that 3 points are invariant to scale. So instead of using just distances, if you take 3 points and you just divide by the perimeter of the triangle, this is invariant to scale. So you don't have to worry at all, but it's more expensive. Looking on higher order, it's doing better job on modeling, but it's costing you a lot of time and computational complexity.
Well, thank you very much again. I'm sure people are waiting for coffee.